My name is Zhenxiao, and I'm from UC Riverside. So now this memory forensics refers to a structural analysis of volatile memory bytes acquired from various devices, such as the PC, cloud VM, smartphones, or even IoT devices. And what makes it different from traditional digital analysis is that we can reveal artifacts that only exist in the memory, such as the running processes, open files, network traffics, or even loaded kernel modules. And we can, well, based on these artifacts, we can perform further analysis, such as kernel rootkit detection or malware detection. So this figure presents a typical process of memory forensics. We first capture the RAM content from the target system. Then we dig out the forensics artifacts from the raw bytes, including like the running processes. And all these artifacts are managed in some kernel data structures. And one important question here is, how can we bridge the semantic gaps between the raw bytes and forensics artifacts? In order to do that, we need what's called a kernel profile. Well, it is essentially a map of kernel data structures, including the addresses and the offset of fields in the objects. With the help of the kernel profile, we can reveal memory residential information. For example, if we want to examine a running process status, we can follow the init task symbol and locate the very first task structure in the memory. Then, according to the offsets of the fields, we can read out the value in the memory. For instance, this comp field represents the process name. If we read the value at the offset of 2584, we can get that this process is a swapper process. And similarly, we can analyze the process memory by reading the MS structure or the open files by reading file-related data structures. Well, traditional approaches try to generate a profile by compiling a kernel module in the target system and emit the debugging symbol as a profile, which contains all the offset of object fields. However, well, imagine the following situations where you want to do a crimson postmortem, where the investigator only wants to acquire the memory of the devices without leaving any traces in the device. Or for IoT or embedded devices, the compiler toolchain or kernel headers may not be installed in the system. Or for cloud providers, they typically do not have permissions to access the customer's system. So in the above situations, which is referred to as binary-only memory forensics, traditional compilation-based approach would fail. But still, we have to generate a profile for Linux kernel because Linux kernel profile is not reusable. Well, the kernel itself upgrades very frequently. So between the versions, the object layouts will be different. And also, even for the same version, since it's highly configurable, like if you compile the kernel with different configurations, you will get a very different kernel object layouts. So to tackle that problem, this is the overview of our proposed approach, LogicMEM. So we take the memory dump as an input. Then we first use a signature-based searching method to recover the kernel symbols from the memory. Then after we find the kernel symbols and locating the objects, we use a logic inference approach to infer the offset of forensics required fields. And the idea of logic inference is quite simple. So, like for instance here, we have a bunch of basic facts in the knowledge base, like Tom is the father of Sally and Tom is the father of Eric. Then we define a bunch of logic rules. For instance here, we define the sibling rules to be, these two persons have the same parents. Also, we define the parent-child rules to be, well, it either is the father of this child or the mother of this child. So with the logic rules and the facts, we can then make some queries such as, is Mike the father of Tom? Then the inference engine will like going to the knowledge base, if we can find a valid facts, then it will return true. Also, we can make queries like, who is the father of Tom? Again, it will go into the knowledge base and try to find every valid entries for this query. In this case, it is Mike. Then like we can, make queries about the logic rules, like whether Sally is the parent of Tom. In this case, it cannot find any valid facts that satisfy this logic rules, so it will return false. Similarly, we can make queries like who has the parent-child relation. In this case, it will basically return every candidate that satisfies these rules. So with this being said, what we want to do is we predefine a bunch of logic rules just like this for the fields we care about, and we collect some basic facts from the memory. So then we let the inference engine to do the job and locate the offset of fields in the memory. So to do that, we first need to collect some basic facts, since the raw bytes are not so meaningful. And what the fact collector does is it lifts the raw bytes into some lower level facts, such as the pointers, numbers, and strings. So it basically decodes the values at each aligned 8 bytes alignment or 4 bytes alignment, and then it conservatively predicts its type to be pointers, numbers, or strings. And the collected facts include the offset of this value, the type of this value, and the value itself. Then the logic inference is performed over all the collected facts and the predefined rules. So you can view this process as an optimized search over a finite domain, in which the finite domain is the collected facts, and the optimized meaning this is guided by the logic rules. And so the result of the inference process will be the offset of the candidate fields. So here, the logic rules plays an important role, and the better logic rules you have, the less false positive or false negative you will get in the inference result. Then the big challenge is how can we define a good quality of logic rules? According to our kernel evolution analysis over 47 major Linux kernel versions, we found that there are always invariants in kernel data structures, meaning that some fields remain stable and unchanged among the kernel upgrades. And here we define the invariant features as those fields that do not have any type changes or name changes or reordering, and they always exist in the object definition. So here, this table shows some results, and you can find more explanations and results in the paper. But one major takeaway right here is the fields required to perform forensics analysis is only a small portion of all the kernel data structure, kernel fields. And this forensics required fields has minimal changes over kernel upgrades. So we can confidently use the invariant features of those fields to construct the logic rules. And here I'll show some simple logic rules we have. For instance, first we have the type invariance, which means like for the task structure, for the tasks field, it always be a pointer. And also for the comp fields, it is always be a string. Another type of type invariant is the pointer type. And this basically means like the MM field and active MM field, they points to another valid data structure, which is the MM structure. So we will have another set of rules for the MM structure. Also, the order invariance, this rules right here basically defines, basic means the tasks field is always defined before the comp field. And another type of strict order invariant is the adjacency invariant. This basically means these two fields always have a fixed offset between them. And then the range invariant means the offset of those fields is bounded by the size of this data structure. And a special type of invariance is the value invariance. Although it cannot be observed directly from the source code, but we can still have some value invariance based on heuristics. For instance, the arc start field and arc end fields points to the beginning and the end of command line arguments. So we can naturally have rules like the value of arc start is less than the value of arc end. And you can definitely find more logic rules and explanations in the paper. So for the evaluation, we first evaluate LogicMEM on mainstream Linux distributions. We collect kernels from CentOS, Debian, and Ubuntu, and the kernel versions ranges from 3.10 all the way to 5.10. And the result is quite promising. We have the LogicMEM has no false positive and negative over the mainstream Linux distribution. We then compiled a set of Linux kernel with the random configuration. So in this way, the configuration is basically a randomly determined. So the resulting kernel object will be very different. Even in this case, we can still have a perfect precision and an average of 95% recall rate. Then we also do some evaluations on real-world cases. We collected kernels from Android smartphones and other router firmware such as the OpenWRT and the LADE. In these cases, the compilation-based approach fails because either there's no compiler toolchain or kernel header available in the target system, or you will get permission denied by simply compiling a kernel. But still, we can generate a valid profile directly from the memory dump and perform some basic forensics analysis. And this screenshot shows that with the generated profile, we can list all the process memory layout for this Goldfish Android kernel. Also, we can list the running processes for this OpenWRT firmware. And also, we can list all the loaded kernel modules for this LADE router firmware. In terms of the performance, well, for our 4 GB memory bytes, the end-to-end performance is around 2 minutes. We also found the memory dump size does not affect the time we do the logic inference. It only affects the time where we're locating the kernel. But since other systems has KASR enabled, so basically the kernel is randomly located in the memory. So in summary, we presented a novel approach to binary-only profile generation. And we show that LogicMEM can achieve a high precision and recall within a reasonable efficiency. Also, we do evaluations on the real-world cases and show that the generated profile can support some basic forensics analysis. And our project is open sourced. You can find the code and the logic rules in the BitSecure Lab Git repo. Thank you very much, and I'll be happy to take any questions you have.
Yes, thank you for